I'm Andrew Jackson. I'm an economic geologist with Sprott, and I focus on technical evaluations of the mineral companies and properties that Sprott invests in. I've put together this Ore Deposit 101 series of talks to help non-technical people understand ore deposits. The talks highlight some of the features of the main deposit types that investors in the resource sector may come across, and provide an introduction to the jargon you will find in press releases put out by exploration and mining companies. This is the 10th talk in the Ore Deposit 101 series, and it focuses on the exploration process. The previous talks in this series have focused on the genesis of one or more ore deposit types and included just a short section on how we explore for that type. This talk reverses that emphasis. It focuses on how explorationists develop an exploration strategy, how they develop an exploration model, and design an exploration program, and select the optimal exploration tools to carry out that program. As usual, the talk will end with a series of learning points from this talk. There are two fundamental truths about the exploration industry. The first is that most exploration programs are doomed to failure. It's been estimated that only 1 in 5,000 or even 10,000 raw prospects will eventually be shown to hold deposits that can support a viable mining operation. Therefore, the odds are that the vast majority of exploration programs will end up with nothing to show for the dollars expended. The second fundamental truth is that most explorationists have more ideas than they have funding to test those ideas. These two truths mean that simply playing the odds and drilling hundreds of targets is a shortcut to financial ruin. If they aim to be successful, companies need to develop their exploration strategy with a huge amount of thought and research. The old adage of failing to prepare is preparing to fail holds particularly true to the exploration industry. Before I talk about designing an exploration strategy, I want to touch on how the exploration industry has changed over the last 10 years, and how the balance between the majors and mid-tier and junior companies has shifted. 10 years ago, the majors carried out most of their own exploration, focusing on the search for very big deposits that they could mine themselves, while keeping an eye on the juniors just in case one of them stumbled over something big enough to be of interest. A few majors did in fact buy out juniors that had made huge discoveries, such as Diamond Field's Voisey's Bay or the Hemlo discovery, but most preferred to do their own exploration. But over the years, the majors, in an attempt to reduce risk, decided that they would rather pay more for a genuine discovery by a junior than to carry out their own, and often fruitless, exploration. The majors virtually ceased regional exploration, and were focused entirely on their exploring for extensions and satellites of deposits that they were already mining, an activity known as brownfields exploration, or MINEX. In the last few years, the mid-tiers started following suit. Some of the major and mid-tier companies bought advanced projects from juniors only to find that they didn't live up to expectations, such as Kinross's purchase of the underworld's white gold discovery in the Yukon, or Redback's Tasiast in Mauritania. Or they found that the politics of the country where the deposit is located changed for the worse, as in the case of Fruta del Norte deposit in Ecuador, which Kinross bought for almost $1 million, and then walked away from when the Ecuadorian government enacted outrageous mining legislation. At the moment, most of the majors and mid-tier miners are so risk-averse that none of them seem to be interested in doing their own exploration or doing any acquisitions. Their boards and management seem paralyzed by fear of failure, an attitude which will cost them dearly in the long run. Mining is a high-risk enterprise, and as the British SAS motto says, who dares wins, or you snooze, you lose. But generally, much of the exploration industry is now supported by the efforts of the junior exploration companies, with the majors depending on the juniors' discoveries. But there's a problem with an industry model that relies on juniors. Most of the easy targets have been found, and many of the juniors really don't have the technical skills to explore for the more difficult targets. In addition, whereas the majors used to have a reasonably assured and relatively stable funding to be able to take on long-term high cost and high-risk exploration, most juniors have neither of these things, living a hand-to-mouth existence. So the result is that there is a lot of money wasted on easy but worthless targets that really have no chance of proving economic for a major miner. I call it chicken scratching exploration. There are currently very few companies that have both the steady funding and internal skill set and vision to take on the job of exploring for the next generation of big mines. Friedland's Ivanhoe Mining is one of the few companies operating in this ever-growing void between the majors and juniors. Okay, so now let's return to how an exploration strategy is designed. There are initially three very simple questions that need to be answered before the strategy can be designed. What commodity and deposit type are we going to look for? Where are we going to focus our efforts? And how are we going to explore? The answer to the first question is often driven by market cycles. Which commodities have a perceived or anticipated supply shortfall? When the uranium price is rising, every man and his dog is setting up a junior explorer to look for it, whether or not they know anything about uranium. On the other hand, when Fukushima was destroyed by the tsunami and the public's knee-jerk reaction caused governments to close down nuclear reactors and cancel others under construction, no new uranium companies were listed on the stock markets. A serious exploration strategy has to be much more far-sighted than this, as it may take 6 to 10 years for a discovery to be made, deposits to be delineated, feasibility studies to be carried out, permits received, construction completed, before the production can actually begin. History is littered with discoveries that didn't make it until the following cycle, because the discovery came at a time when commodity prices were declining. Once it is decided what commodity to focus on, we have to decide on what ore deposit type to look for, and where they occur. As we've seen in earlier Ore Deposit 101 talks, most commodities can be found in more than one class of ore deposit. Deciding which one or ones to search for should depend partly on the skill set and the experience of the explorers. Too often I see companies with good technical people switching their efforts to a deposit type that they have no experience in, simply because it is the flavor of the month. Some discoveries are serendipitous, with luck playing a huge part, but the majority of discoveries come out of hard work and a deep understanding of the mineralization controls of a particular class of ore deposit, and the geology of an area that they occur in. Selection of where to focus efforts is the primary decisions that the strategy is built on. Focus where the geology and the tectonics are right for the type of ore deposits that you're seeking, and where your team has experience, both technically and commercially. The answer to the final question about how we explore for the commodity of interest is answered by building a genetic model and an exploration model. Now, what's the difference between these two? A genetic model builds up an understanding of how the deposits form and what are the critical controls on the mineralization. So we need to ask questions such as, what are the preferred host rocks? Are they structurally controlled or stratigraphically controlled? Is the fluid temperature a critical issue or not? What sort of hydrothermal alteration are they associated with, if any? What are the associated minerals? Is there a preferred time period when the deposit's formed? What sort of dimensions are the deposits likely to have? And 100 similar considerations. The aim of the genetic model is to end up with a mental picture of the deposit you're looking for, how it forms, and what its physical characteristics are. Only once this step has been done, and we know the physical characteristics, can we select the right exploration tools to detect the characteristic features of the type of deposit. Genetic models are often criticized as being too academic and are being of no value to a really pragmatic explorationist. This is partially correct. Genetic models as an end to themselves are of only very limited value. But they are a vital means to an end, and that end is the exploration model. The aim of the exploration model is to match certain of the physical characteristics defined in the genetic model to available exploration tools that can detect those physical characteristics. So, for example, if you determine you're going to be looking for copper porphyries, your genetic model will tell you, among other things, that the mineralization occurs as discrete disseminated sulfide particles in a stockwork of fine quartz stringers. There's therefore no point in using electromagnetics or EM to explore, as this will only detect massive sulfides. Instead, you would use induced polarization, IP, which is very good at detecting disseminated sulfides. In the same way, you would know that porphyry mineralization is usually associated with potassic alteration, and that's characterized by the presence of potassium feldspars, secondary biotite, and magnetite. A magnetic survey ought to be able to detect the magnetite, and hence, indirectly, the best host for any associated copper mineralization. I'll talk more about the exploration model shortly. There are a number of points that need to be borne in mind during the process of designing an exploration strategy. Let's discuss these. Some explorationists who used to practice their profession in the big mining houses that have deep pockets go about exploration with the any information is good information approach. They say, let's collect a full spectrum of data and then we can decide which data sets are of most value. But you'll remember that one of the fundamental truths that I mentioned earlier is that most explorationists have many more ideas than they have funding to test those ideas. Most mid-tiers, and certainly all juniors, are limited by their budgets. They have to be much more surgical in selecting which data sets they spend their budgets collecting. They need to ask themselves, what are the key questions that I need to answer? And is my proposed program focusing on those questions? If the answer is no, but just that it would be nice to have the data, then that work should be scrapped, or at least put on ice. We need to clearly define decision points of the program before starting. When I ask exploration managers, what would make you walk away from this project? And I get an answer, I can't answer that until I've seen what the data tells me. Warning bells go off in my head. This program has not been thought through, and its budget and timeline are likely to slip. Likewise, I want to see a clear, measurable decision points. For example, the statement, I want to show the clear evidence of a potentially economic mineralized system, doesn't cut it. An answer like this provides too many loopholes to allow a dog of a project to continue to be funded. I'm looking for something along the lines of, if I don't intersect at least 10 meters at 1 gram per ton gold in 3 of my 8 holes, I'll need to walk away from the property or completely rethink this program. It's quite possible that a drill program will blow one hypothesis out of the water, but it will show that another hypothesis is worth testing. Hence the validity of the or completely rethink this program clause. But this has to be stringently applied. And this brings me on to the last point in this slide. Exploration programs do have to be kept flexible. New data is coming in the whole time and the program should be refined as that data is absorbed. It's astonishing how often I see big drill programs, some lasting many months, being doggedly carried on as originally designed, even though the early holes show that the underlying hypothesis is clearly flawed. Exploration budgets should always be conditional on success and should be regularly reviewed and reprioritized. Finally, although perseverance in the face of adversity is important, Beware of the company that has evidently fallen in love with their project and is blind to the growing evidence that it's a dead horse and one that they should have stopped flogging long ago. So there are some of the pointers on how exploration strategies are constructed. We've now decided what commodity are we going to look for and where are we going to focus our efforts geographically. Now we need to use that exploration model that we constructed to decide how are we going to explore for our chosen target. Which exploration tools are we going to choose to take along with us? And much of the rest of this talk will focus on this question. The difficulties of mineral exploration are sometimes compared to a blind man trying to describe an elephant, when all he has to go by is the small portion of the elephant that he can touch and feel. At best, only a small portion of an ore deposit is visible at the surface, and increasingly the ore bodies don't outcrop at all. So the job of the geologist is to take the clues that can be collected by the various exploration methods and come up with a mental picture of what the deposit may look like, and then to test that hypothesis using the most time and cost-efficient processes he can. In many ways, exploration is also like playing golf. When you play golf, you choose your club to suit the task and the terrain. A driver to get into the right area, a chipper to get into the sand, into the green, a sand wedge to get out of the traps, and a putter to sink the ball. In the same way, during exploration, the selection of the correct exploration tool depends on the stage of the exploration, the features of the deposit type from the exploration model, and the exploration environment. So let's start with the stage of the exploration project. There are several ways of classifying exploration programs, i.e. a program that has not reached feasibility study. But most divide the process into three. Phase 1 exploration, also known as early stage, generative, or grassroots. At this stage, the objective is to define the geographic area of focus, identify signs of mineralization for follow-up, and identify drill targets. Programs at this stage will require regional targeting tools, and I'll go into these in some detail shortly. Phase 2 exploration, also known as mid-stage or evaluation. At this stage, the objective is to determine if the target has the potential size and grade to be economic. Programs at this stage will require focusing tools, including reconnaissance drilling. Phase 3 exploration is also known as exploration advanced stage or delineation. At this stage, the objective is to delineate the resource of the target and to complete a scoping study or preliminary economic assessment, PEA. This requires detailed drilling, resource estimation, and preliminary engineering and metallurgy, the selection of possible mining method, and preliminary financial estimates. Having established what stage the exploration program will be, the next factor to be considered in selecting the exploration tools to be used are the features of the targeted exploration deposit type. This is where we return to the exploration model that we constructed. The model has defined the likely characteristics of the ore body we are looking for, and we need to select tools that can detect those characteristics. Some characteristics can be detected directly, such as magnetics, e.g. the magnetite in iron deposits, or radioactivity in the case of uranium deposits, or electromagnetity in the case of massive sulfides, and these are relatively straightforward. But other deposits do not have any characteristics that can be directly detected by geophysical methods. This is where the exploration geologist has to think laterally and look for exploration techniques that can detect features that may be just associated with the mineralization. Examples of these include magnetics to detect the presence of faults that may have acted as channelways for hydrothermal fluids, or gravity to detect a particularly heavy host rock, or lighter than average alteration. In other words, the exploration tool model tells you which features to look for, and so which techniques to use. The third main factor to consider in selecting exploration tools is the nature of the environment that you'll be working in. Here too, the geologist needs to ask himself a number of questions. For example, is the weathering likely to be deep or shallow? This is significant because the geophysical and geochemical characteristics of the original primary ore change as the mineralization is oxidized. Is there sufficient cover? Sufficient cover might mask radiation and obscure or disperse geochemical anomalies. Is the terrain mountainous or flat? For example, a big vibro-size gravity survey is impractical in a mountainous terrain, and rough topography will also limit airborne surveys in fixed-wing aircraft, and it may be necessary to switch to a helicopter-borne method. How thick is the vegetation cover? Thick tree canopies can mask infrared spectrometer surveys, and thick mulch in tropical forests can make soil sampling very difficult or impossible. What are the climatic conditions? High rainfall in the tropics will result in a very different soil profile from one in the cold, high Arctic, and the geochemical techniques need to be adapted accordingly. For example, in the latter case, stream sediment sample might need to be replaced by till sampling. Each of these issues, and many others, will contribute to the selection of the most cost-effective exploration tool for the job. Now, this table summarizes the most commonly used exploration tools that are available to exploration teams. It also shows which tools are employed in Phase 1 in green, Phase 2 in orange, and Phase 3 in red exploration programs. We'll go through this list discussing each of the tools, starting with the first of the Phase 1 tools, the widest seeing technique, satellite imagery, and air photography. Stereo air photo interpretation used to be the foundation of regional exploration. It's now underutilized, but it's still very, very valuable with trained specialists, and I don't think it is used enough nowadays. In the last 20 to 30 years, satellite imagery has edged out air photos, particularly a technology called Advanced Spaceborne Thermal Emission and Reflection Radiometry. Fortunately, this mouthful can be abbreviated to ASTA. ASTA data is collected from a satellite with a 700-kilometer sun-synchronous orbit. Different minerals absorb different wavelengths of infrared light and reflect others. A sensor in the satellite detects the frequencies of the reflected light and uses this information to identify the minerals present. The method has a relatively coarse resolution, with individual pixels being 15 meters square. Airborne infrared scanners mounted on much lower flying aircraft can improve this resolution considerably, but the data costs much more to acquire. Infrared imagery is very useful for picking up widespread hydrothermal alteration, and it can differentiate between various clays, even though clays are usually too fine-grained to identify by eye, even with a hand lens. Mineralization that's associated with large alteration zones such as porphyries, high sulfidation epithermals, VMS deposits, and Carlin deposits can often be detected with these technologies. You'll remember this example in the Escondido deposit from the Ore Deposits 101 talk I gave on porphyries, where the pink color is reflecting the presence of potassium feldspars, indicative of potentially ore-hosting potassic alteration. Down the list, airborne magnetic surveys provide a very quick and relatively cheap method of collecting data when measured on a per square kilometer basis. Recently, there's been increasing use of ultralight aircraft, and pilotless drones with miniaturized equipment as instrument platforms. These surveys can detect magnetic rocks through cover. The method is great for exploration for buried magnetic ore bodies and host rocks. And here you can see, for example, a featureless part of the southern Botswana, completely blanketed under a thick cover of wind-deposited Kalahari sands. You can see nothing, but when the magnetic data is superimposed, the hidden kimberlite intrusions become apparent. Magnetics is also useful for identifying potassic alteration in porphyries and defining faults under glacial cover, for example in many Canadian greenstone belts. Radiometric surveys are often flown at the same time as magnetics, but a radiometric survey needs a full-sized aircraft. The scintillometers are heavy. The survey measures radiation from the decay of uranium and potassium and thorium. The response is only from the very surface, with a penetration just a few millimeters. Unlike magnetics or gravity, which can penetrate many kilometers of overlying cover rocks. Radiometric surveys are useful for uranium deposits of most types, but also porphyry deposits to identify the potassic alteration and different phases of the intrusion, as in this example of Mount Milligan, and high sulfidation epithermal deposits. Regional gravity. Some rocks are more dense than others. A gravity survey can detect these subtle differences. Regional ground gravity surveys are relatively slow, expensive to collect, and so they usually have sparse data and poor resolution. But newer airborne techniques, using gradiometers, are changing all this. Here's an image of the Twin Creeks Getchell area in northern Nevada. The southeast half of the image is under younger cover, less dense, poorly consolidated gravel cover, which is why it is slightly blurred and blue, which represents low gravity. Gravity is good for kaolin deposit exploration, looking for upfaulted blocks of heavy carbonate hosts under this gravel cover, and also for looking for calcite destruction. It is also used in exploration for VMS deposits and nickel sulfides, both of which have large quantities of heavy sulfide minerals. Airborne electromagnetics, or EM. There are several techniques of airborne EM, including input, geotem, megatem, VTEM, and ZTEM, but they're all variations on a theme. They basically generate an electromagnetic signal, and then they measure its decay, plotting this variation over the area. Surveys can be done from the ground, but they're usually flown in a helicopter or fixed wing. They're rapid and relatively low cost, although more expensive than magnetics and less direct. The transmitter coil can be on the ground or on the aircraft. The receiver is usually towed in a bird. The system detects conductive rocks, and so it's useful for exploring for VMS, SEDEX. The example on the slide is the Sullivan deposit in BC, massive copper-nickel sulfides, and iron ore. Of course, false anomalies are also common, especially coming from graphite. Now, in geological mapping, all the previous exploration techniques are remote methods that can be carried out without even putting a foot on the ground. Geological mapping is a direct technique, and it is a critical part of most exploration programs. Boots on the ground. The aim is to identify potential host rocks, structures, and outcropping mineralization. Geological mapping is the foundation on which other data sets are superimposed. Seismic surveys detect variations in seismic velocities in the Earth's crust, and so only work where there's inhomogeneous stratigraphy. The principle is to produce shock waves at the surface, and then measure the echo as the waves are reflected or refracted off rock boundaries at depth. The initial shock waves are created by explosives or vibration using big trucks that repeatedly drop weights, or simply vibrate large pads in contact with the ground. The echoes are detected with rays of geophones set out on the surface. The data can be either 2D, a single planar cross-section like this, or 3D, like this model. Seismics are useful for detecting structure and stratigraphy, but the technique works poorly if these are steeply dipping. Seismics was originally developed for oil exploration, but now it's used more extensively for hard rock targets than before. The main drawback of the technique is its expense and the delay in processing the data. The main uses are still for oil exploration, where it's the primary tool, unconformity-related uranium, Witwatersrand and Carlin deposits, greenstone shear zone hosted gold, and VMS deposits. Moving on to Pima. Pima is an abbreviation for Portable Infrared Mineral Analyzer. The equipment analyzes the wavelength of reflected light. In other words, it's like a handheld Aster. Its main use is in mapping hydrothermal alteration, as it is capable of differentiating between clay minerals that are too fine-grained to separate by eye, or even using a hand lens. It's valuable for ground follow-up of satellite imagery and the alteration quantification in drill cores and chips. An example of a really successful Pima-based exploration program was Placidome's Kamchatka mapping program. 6 geologists covered a 160 kilometers by 60 kilometer area in just 2 months, collecting representative hand specimens and then analyzing them with the Pima overnight in the base camp. This allowed real-time follow-up and detailed sampling over anomalous areas. The team identified and mapped 5 hydrothermal systems and discovered 3 zones of epithermal mineralization in a single very short summer field season. Stream sediment sampling. This is a quick, cheap, regional geochemical technique that allows you to focus follow-up within areas of the highest potential. It's obviously of limited use in arid areas or in areas of muted topography where there's little or no sediment transport. It's used for a variety of deposit types, including base and precious metals, tin, and chrome. The data in the slide is from Aurelian's exploration target in Ecuador, the ringed areas where the Fruta del Norte epithermal gold deposit was eventually discovered. The other anomalies have not yet been properly explored, to my knowledge. Lake sediment sampling. This is a similar technique to stream sediment sampling, but it's used where there's a high density of lakes, and flat topography means that the streams flow very slowly and they don't transport significant sediment. So this method can be done, used to be done by hand from boats or augering through the ice in winter. But now it's generally done by helicopter, dropping a gravity core sampler. The method has been used for base metals, gold, uranium, and diamonds. Ridge and spur soil sampling. There are various techniques of soil sampling. These include collecting by hand or using an auger, etc. Most take a sample from the C-zone, just above bedrock, and assay a 50-gram aliquot, generally using 32-element ICP plus or minus fire assay. Ridge and spur sampling is used in mountainous terrains where movement is difficult, for example in tropical rainforest. Samples are taken from the ridges as these are not affected by soil creep and they are easier to traverse than the steep flanks of mountains. Till sampling. This involves collecting material that was dropped by glaciers and ice sheets. It is similar in concept to soil sampling, but there's no in situ soil, just transported glacial debris, or till. With this technique, you're looking for a trail of eroded mineralized material that's been dragged and then dropped by moving ice sheets. The example shows copper-nickel exploration in Finland. In this case, the sample spacing is only 1 sample for every 4 square kilometers, so it's a very efficient method of covering area quickly. You'll sometimes hear people talking about BLEGs. This is an abbreviation for bulk leach extractable gold. It's a version of stream sediment or soil sampling, but it involves taking much bigger samples of fine-grained material, say 2 to 5 kilograms. The sample is then leached with cyanide rather than using a traditional extraction and assay method. The technique is aimed exclusively at gold. It requires only very wide sample spacing, and so it's very useful as a first-pass exploration tool. Because of the dilution factors, much lower values are regarded as anomalous and significant than they would be in conventional soil sampling. This particular photo was taken in Mali. Notice the sieve being used to select only the fine material for assay. Grab sampling, also known as rock chip sampling. This is used both in very early reconnaissance sampling to see if there's any indication of anomalous metal values, and also in more detailed mapping. In our golfing analogy, this would be the 5-iron, used to get you close to the green. The actual assay value is not significant. We just need to see what it is relative to the average background value. The sample usually consists of a fist-sized chunk, preferably off an outcrop, but float samples are also of value. Samples are usually collected while mapping, and as you can see, it can be used in most environments. Grid soil sampling. This technique is used in both Phase 1 and Phase 2. As the name implies, it consists of a systematic soil sampling along lines that are 25 meters to 1 kilometer apart. Along each traverse, individual samples are generally taken 10 to 100 meters apart. Contour intervals are calculated using geostatistics. Obviously, the technique requires soil, so it's good in tropical and subtropical areas where good soil profiles are developed. Soil sampling is an excellent way to define the limits of shallow mineralization. There are a couple of caveats. Beware of soil that creep and dispersed anomalies on slopes. Ensure you are sampling in situ soil and not transported soil, and ensure that the samples are taken of consistent material. The sample is usually sieved to collect only the fines. 50 to 100 grams is needed for a reliable assay. The method is used both for base and precious metals, and also white-based soil or till sampling is used to detect kimbolites that host diamonds. You take a large soil sample, sieve it to concentrate the sand-sized portion, and then this is then separated by gravity to collect the heavy minerals looking for kimbolite indicator minerals, or KIMs, which include chromite, chromium diopside, and chrome-rich pyrope garnets. If these are present, then you increase the sample density and use geophysics if the kimbolite doesn't outcrop. The data in the image is of Diavik and Nekati kimbolites in the Northwest Territories. The map covers an area of 200 kilometers by 160 kilometers, and you can see that the samples were taken 10 to 20 kilometers apart, and that this was a sufficient density to draw explorers into that swarm of kimbolite pipes. Ground magnetics is carried out to follow up broad airborne magnetic surveys and to provide a higher resolution over selected areas. An integral GPS automatically plots data as the operator walks along. The technique is obviously of use in looking for highly magnetic ore bodies, e.g. ones that contain magnetite or pyrrhotite, or a reduction in magnetics due to alteration, for example sulfidation of magnetite. It is also useful for defining structure if the mineralization itself isn't magnetic. It can be used for VMS, SEDEX, sulfide nickel, porphyries, iron ore, Archean gold veins, chromite, and platinum group metals. In fact, magnetics is one of the most useful and most widely used exploration techniques. Detailed gravities are used the same way as detailed ground magnetics to fill in detail over selected areas of interest. The example shown is of Monax's Punt Hill property in South Australia, just south of Olympic Dam. You can see the difference in resolution between the area in the northeast and the area in the southwest of the image. Monax actually drilled the anomaly in the white circle, hitting IOCG-style mineralization, although it proved too deep to be economic so far. Gravity is of use with VMS, SEDEX, Carlin, IOCG, iron ore, and kimberlites deposits. Now we start moving into techniques that are generally used in both Phase 2 and Phase 3 exploration. The first of these is IP, or induced polarization. IP is an electrical geophysical method where intermittent current is fed into the Earth and the response is measured through other electrodes. The data includes both resistivity and chargeability. Resistivity measures the ease or difficulty with which the Earth conducts electricity. For example, silicification is highly resistive. Chargeability is a measure of the decay of the signal after the current is switched off. Chargeability detects disseminated sulfides, but not massive sulfides. It's used on epithermals, Archean shear-hosted gold, porphyries, and Carlin deposits. It's not of use with massive sulfides, for example, in the VMS or SEDEX or nickel sulfides. It can reliably only penetrate to a depth of about 250 meters, although some of the newer equipment is claimed to be able to see down to 500 meters or deeper. CSAMT. This is an advanced geophysical technique. CSAMT stands for Controlled Source Audio Frequency Magnetotellurics. It uses the same principle as IP. In other words, it measures the conductivity of rocks. But it uses a much bigger transmitter loop, and so it has far greater depth penetration, down to 3 or 4 more kilometers. CSAMT played a part in the discovery of reservoir minerals, Cukurupeki deposit in Serbia. Self-potential, or SP. This is a very cheap and simple geophysical technique. It relies on oxidizing sulfides, which produce a potential current between them and the surrounding ground. It requires only a very simple galvanometer. No current is put into the ground, unlike with IP. SP is effective if conditions for oxidation are right. In other words, shallow groundwater, warm climate, and high sulfide content in the ore body. But it actually isn't used much, as IP is much more effective. It'll detect massive sulfides better than disseminated sulfides. Now we get to the methods that are used for sampling the third dimension. The first of these is auger. It's really just deep soil sampling, and seldom extends to more than 10 meters depth. It can be carried out with a vehicle-mounted machine or a small handheld machine. Although I've shown it as being used in both Phase 2 and 3 projects, it's most commonly used in Phase 2 ones. The term trenching covers a multitude of sins, ranging from scraping thin moss or soil cover off outcrop to 5-meter trenches in deep tropical lateritic soils. Trenches can be dug by hand or trencher, by excavator or bulldozer. And the aim is simply to expose bedrock for mapping and sampling. Trenching provides a link between the indirect geochemical or geophysical methods and direct soil drill sampling. It's cheap, it's quick, and it provides valuable information on rock type, structure, mineralogy, and grade. It's used on a wide variety of deposit types. Environmental regulations usually require that the trenches are filled in and revegetated after mapping and sampling are complete. Drilling is an indispensable method for exploring the third dimension. The drill rig is sometimes referred to as the truth machine. There are a variety of different drill techniques. Reverse circulation is one of the most common. An RC bit is solid with tungsten buttons. It's attached to a hammer and double-walled drill rods. A compressor blows air down the outer tube, and the drill cuttings are blown up the inner tube. Cuttings are collected from the cyclone, the big yellow cone at the bottom left of the picture. So what are the advantages of RC? It's fast, it's relatively cheap, and has a reasonable depth capability of maybe down to 500 meters, depending on how much groundwater there is. And the disadvantages? Well, firstly, it produces small rock chips only, which yield far less information than drill core. Secondly, there is a tendency to smear grade down the hole. And thirdly, RC does not perform very well in wet conditions, in other words, below the water table. RC is good for large disseminated deposits, where smearing of grade isn't quite so critical. Another drill method that you'll hear about, and is particularly common in Australia, is RAB, or Rotary Air Blast. It's very similar to RC, but it doesn't have the double tubes in the rods, so the sample blows up the outside. Advantages? Well, it's very quick and cheap. The disadvantages? It produces chips only, like the RC. It also has limited depth capability, usually less than 150 meters, and the same poor performance in wet conditions as RC. But most importantly, it is prone to contamination from the sides of the hole. RAB is often used for ore delineation in open pit mining operations. Oil and gas drill rigs are some of the simplest in theory. Collection of sample from the hole is not critical, except for identification of stratigraphic position, and is only the drilling to test for the presence of hydrocarbons, and then to provide a well to extract the oil or gas. So it just needs a bit and a way of pumping the fluid or mud down the hole to flush out those cuttings. Although simple in theory, oil rigs are enormously complex pieces of equipment, partly because of the depths that they drill to and the marine environment that they often operate in. Drill holes are large diameter, usually 5 to 36 inch in diameter. And it can attain a depth of up to 25,000 feet. They're usually fitted with steerable bits, which allow deviations of the hole to turn the hole in a certain direction or to flatten it to horizontal. Once a production well is drilled, the rig is replaced with a much simpler production platform. Lastly, diamond drilling or core drilling. This is the ideal method for most exploration, but is generally about 3 times the cost of RC per meter. The phrase diamond drilling refers to the drill bit, which is studded with industrial diamonds in a metal matrix. It produces a core of solid rock, which provides much more geological information than RC trips. A diamond drill can reach between 300 and 4,000 meters, depending on the rig type. In a wireline rig, the core is collected in a core barrel and hauled up the center of the drill string after every 5 to 10 meters without having to extract the entire length of the drill rods. This speeds it up enormously. Diamond drill core is usually split or sawn lengthways. Half goes for assay and half is kept as a record. Diamond drilling is essential for drilling narrow vein deposits, as there's no downhole grade smearing as there is in RC. It's also valuable for structurally controlled deposits such as Archean shear zone hosted gold and VMS deposits. So that is the end of the list of the more common tools available to the exploration geologist. Exploration is a process of logical hypothesis building and testing, and exploration tools have to be chosen carefully to allow the most efficient testing of the hypotheses. No single tool will lead you to the deposit. There is no single silver bullet. Groups of tools are used in combination to rule out or prove possibilities, moving steadily from the big picture hypothesis to the more detailed data collection to a final discovery. Because of the variety of data sets that need to be compared and combined, GIS technology, or geographical information systems, which allow for the combination and the interrogation of varied data sets, is essential. GIS is the glue that holds the parts of an exploration program together. To my mind, along with the development of 3D computer modeling, GIS can be considered to be one of the biggest single advances in the exploration industry in the last 25 years. Okay, so let's end up now by going through the main learning points that came out of this talk. Firstly, majors are yielding the exploration function to juniors. This is good and bad. Good because the juniors are lighter on their feet and maybe less wasteful in their expenditure. Bad because only a small minority of juniors are both truly competent and sufficiently well-funded to do anything more than shallow chicken-scratching projects. Very few groups are now doing long-term exploration programs for big conceptual targets. Exploration consists of a series of systematic steps, focusing in from the broad scale to detailed testing. In this process, the exploration geo has to define both a genetic and an exploration model. He has a wide range of tools to choose from. The selection of the appropriate tools depends upon several factors: the stage of exploration, the geological characteristics of the ore body, and the environment of the project. Exploration needs a rigorous target selection. Nobody can simply play it as a numbers game. The odds of success with this approach are far too long. The program design needs to identify the hypothesis and the tests required to improve or disprove that hypothesis. And finally, clear decision points are needed to avoid target creep and wasting of funds on dead horses. And finally, strict budget control. So that's the end of this talk on exploration process. The next talk in the Ore Deposit 101 series will be on ore resources and reserves, and it'll deal with how resources and reserves are delineated and projects evaluated, so that we can reach the decision to either build a mine or abandon the project. The answer to the question, in short, can we make money from this pile of dirt?